speaking about improving network reliability with partial discharge monitoring. Webinar will be recorded, and if you have any question, please put them in the chat box and unmute and ask at the end of the webinar. And if you are expert or having suggestions for others to speak at our DIS monthly webinar, please reach out to us, the Matthews or Sneha, or you can contact me as well. Today we are having Neil Davies. Neil is the Managing Director of EA Technology Australia, a chartered engineer and the member of IET. Neil has over 25 years of experience in the electrical engineering sector, an innovator who led the development team that won 2 UK Queen's Awards for innovation. He played an integral role in the development of non-intrusive condition monitoring tools for high voltage assets. Neil was the group commercial director of EA Technology before leaving the UK headquarters in 2014 to take over and lead Australasia and Asia Pacific side of the business. Here is the abstract. The use of instruments to detect and measure partial discharge activity is well established as a way to identify HV substation assets which are in danger of failing. Regular surveying of substations for PD activity every few months or annually has been adopted by many companies as an important part of their asset management before practice regimes. Many have also chosen to deploy permanent or semi-permanent monitoring and alarm systems to provide alerts of critical PD activity 24 hours, 7 days in a week. Each of these options has its advantages. So which should be chosen? And what are the drivers informing these decisions? The webinar will discuss how different types of defects can be manifest and how the period from time the condition indicator can be detected to when failure occurs can vary significantly. The business decisions driving different adoption methodologies will be explored. Real-life examples and the case studies will be presented from the application of periodic surveying using handheld equipment through the temporary and permanent monitoring solutions installed onto HV switchgear and cables. The webinar will show how different network operators have approached the challenge and determined the best way forward to meet their objectives and deliver tangible benefits to their organizations. Now, I'm going to stop sharing. Yeah, Neil, can you share your slides, please?
I can.
Still can't?
Which is always good. Okay, everybody good with this?
Be able now, Neil. I've made you the presenter.
Okay, I will share. Okay.
Yes, Neil, go ahead.
No problem. Okay, thanks very much for that. Technology and all that. Webinars always more difficult than real technology that we use every day on the network, I think. So improving network reliability and partial discharge monitoring. So what we're going to cover today, we're going to start with very basic stuff on condition monitoring and partial discharge and why we do that, why we test. And then really what I wanted to cover more today is the whole question which everybody's asking. Nobody's really, when they're asking for a partial discharge test or they're carrying out a partial discharge test, nobody's really after what is the dB value, what is the picocoulomb value. What they're really after when they've got an asset already installed is the question of when will it fail and do I need to do anything about it? Do I need to maintain it? When I take it out of service, will it still give me reliable service in situ? So that's the question that everybody's really asking. So we're going to start looking at that. And we'll look at different testing intervals and different regimes that people do. Because again, one of the common questions when companies start employing or deploying the testing techniques in partial discharge or any condition monitoring is how often should I do it? And it's always a balance between how often catch whether you can catch failure. We'll really explain that through real case studies, so we can show a couple of examples of where failure had happened or would have happened, and what different scenarios will catch them or not. Summarize and of course any questions at the end or in the chat. So very briefly on condition monitoring and partial discharge. I know it's based on the audience. I'm sure everybody's familiar with the definition of what partial discharge is. The IEC definition here, 6270. It's these small spikes of electrical discharges that bridge part of the insulation and start eroding the insulation until we get to the stage where the insulation cannot cope with the stresses and we get a full catastrophic breakdown. So these very short spikes are what we're really trying to detect. And when we're looking at partial discharge, not all partial discharge is the same, and depending where it is on the insulation system, the characteristics and behaviors are can be very different. And that's always a challenge when it comes to the question of when will it fail. So characterizing it, the three major classifications of partial discharge would be internal discharge. So that's simple stuff that's happening deep inside the insulation. So this could be as we can see in the diagram here on the top left, we can have it in the center of insulation. We can have it towards one of the conductors. They will give you different characteristics, but ultimately that's stuff that's happening inside. Often I characterize that as one of the most dangerous types of insulation or PD classifications for switchgear in particular, because it's the sort of thing that you're never going to see, never going to smell, you're never going to hear any fizzing, crackling, you're never going to smell the ozones, nitrous oxides that are developing if it's deep inside solid insulation. So sometimes the first indication of PD, if you're not doing any testing, is that it disruptively fails. So internal discharge is often characterized by quite high amplitudes of discharge and a relatively low repetition rate. So you'll get a buildup of stress across that cavity, and then it will effectively break down like a capacitor breakdown, and that will give you a burst of energy. So it will happen 1, 2, 3 pulses per cycle on the rising falling edge of the sine wave. So quite high energy, relatively low repetition. The next, and what is possibly the most common type of discharge, where you're looking at air insulated switchgear in particular, is discharge that's happening across the surface of insulation. So as soon as we moved away from away from porcelain insulation towards more polymeric insulations in the 1970s and 80s, and going away from compound insulated cable boxes to dry terminations, we started seeing an upsurge in surface discharge activity and problems occurring that way. So this is where you're getting the discharge breaking down across the surface of insulation. That can also be phase to phase if you've got inadequate spacing, say in cable terminations. And it characterizes quite differently to internal discharge. Often you're going to get relatively low levels of amplitude of discharge, but lots and lots of pulses of it. So if you look at picocoulomb sort of range, whilst you might get hundreds or thousands of picocoulombs and an internal void as it builds up and collapses, on surface discharge, this can be down, a serious level of discharge can be down in the tens of picocoulombs, and it is greatly affected by the environmental conditions. So it's two very different characteristics of partial discharge activity. The third main area is corona discharge. So that's from a sharp point into a gas, typically in air, often not a problem. So if we have that on an open terminal switchyard, then we're really not that particularly bothered about it. It might round off some edges, but all the gases that will be generated will dissipate, and it doesn't usually cause you too much of an issue. However, if we put that corona discharge inside a sealed box in metal clad switchgear, then what's happening there is that the byproducts of the discharge, so the nitrous oxides, the ozone, will combine with the moisture, produce nitric acid, and start attacking other insulation, and typically transfer over to the surface discharge, and that's where it causes problems. And the last type of discharge that we come across relatively frequently is sort of an intermediate state between the internal and the surface discharge. So it's like a gap discharge, floating metalwork. It can be called contact discharge. And this is where you get quite high levels of pulses, usually high amplitude and high numbers of pulses of activity that spark across a defined gap. So you end up with another distinct type of characteristic, some of it with the internal discharge characteristics of quite high amplitudes often, and some of the surface discharge characteristics of a quite high repetition rate. If we see that in an open terminal bus bar, switch yard, then again, not often a problem. It may just be the bus roller that is just sitting slightly off and everything not 100% bonded. It causes us more interference and it causes us a problem. If that's on a contact inside maybe an 11 kV cable termination, plug-in termination, then that would be a problem that we would need to address. So one size doesn't fit all when it comes to partial discharge. We have very different characteristics and we have these different types and classifications. So if we've got much different classifications, that's just one set of variables which shows very much difference. And then on top of that, we've got what's the insulation system and what's the voltage, what's the stress, and everything else. So it makes that question quite hard. When will it fail? Now, in order to detect these problems, the ones that are typically used in practice in the field are, or the technologies that are used are in the electromagnetic space. So transient earth voltages, which will be working in the 2 to 80 megahertz region typically. And that's very good for detecting internal discharge, and it will also detect high-level surface discharge to earth. When we're talking about surface discharge, because we get a relatively low spark of energy, then we may not get enough to generate these high electromagnetic pulses that we can detect using the TEV method, the transient earth voltage method. So then we started back in the early 1990s introducing complementary technique of ultrasonic alongside transient earth voltage to detect the problems that we were seeing on surface discharges. So ultrasonic, particularly airborne, if you've got an air passage from the outside to the inside, is the most sensitive. And then there's also contact probes that are used for detecting that inside termination in sealed chambers. Another technique that is quite widely used and more used on cable systems, but certainly can also be used for detecting problems on switchgear as well as cables, is using high frequency current transformers. And these would be typically installed around the earth screen of a cable termination, if you can get access safely, of course. And they will detect also the high frequency current pulses produced from the cable discharge, or if you put a high pass filter in there, that will also detect stuff that's local in the switchgear itself. And finally, the other technique which is used, and there's lots of research you see around this, the UHF technique. UHF is in for medium voltage, high voltage in terms of the, say, 6.6 up to 3366 kV. UHF is not the preferred method for detecting on metal clad switchgear unless you can get inside the metal cladding, you put in sensors inside. For open terminal switchgear, it can be very good because it becomes, you can use it for directionality of finding internal discharge and high level surface discharge, where the transient earth voltage, which is operating in the HF to the VHF range, will basically swamp a yard. There will be lots of signals everywhere, and you can use use UHF to you can use UHF techniques to to basically localize where things are coming from. Also, where TEV probes cannot be used, where you cannot actually place the capacitive sensor on the side of the outside, then UHF is another way of using UHF antennas, another way of using the electromagnetic technique more from a distance. So they're the techniques. So that's really the background that I want to talk about. But today, my focus more on so why are we testing and when will it fail? So we test for partial discharge, and companies, electricity companies, any high voltage user will use PD testing or all condition monitoring to reduce the level of risk that any network carries. It's all about risk management at the end. So if we think about risk is the probability of failure multiplied by the consequences of failure. And the consequences are not always the same. So you might have a minor failure, you might have a major. So when you're actually doing risk calculations, we typically will say that the consequences of failure is the criticality factor multiplied by the average consequences. So minor failures or major failures. But if we just think about this, the top part of this graphic here, risk is the probability of failure multiplied by the consequences of failure. And the consequences and criticality factors that we deal with on any network are all to do with network performance. So I've got an outage, downtime, or SAIDIs or SAFEs on the electricity network. There's always a safety aspect, of course. If you've got a catastrophic failure, as we can see in the bottom right there, if you're in the vicinity of that when that happens, then there's a significant safety issue. So we need to be dealing with that. There's definitely a significant financial issue if you've ended up with a substation that looks like the bottom right graphic. So the financial issue of letting things fail, it's always a more expensive exercise to fix after failure than it is to prevent that failure by intervention. And of course, there's environmental aspects of criticality if we're releasing oil into the environment or burning oil and gases, for example. So where does partial discharge and condition monitoring play in that reduction of risk? Well, it's not changing the asset condition. So in order to change the asset condition and reduce risk, you need to maintain. But where it's really playing in this is it's reducing the probability of failure. So condition monitoring, online monitoring, will, if you act and intervene, reduce that probability of failure. If you're not going to act, you're not going to take heed of the data that's coming from your testing, then there's probably no point in doing it. But this is where we're doing it. So we're looking at reducing the probability of failure. Other ways that we can reduce the risk on the network, of course, is to design it right, and network automation, so that we can mitigate against the consequences of any particular failure. But condition monitoring is reducing the probability of failure and then allowing you to intervene in that maintenance strategy. But ultimately, why are people doing it? It comes down to the three reasons, and they're all very intertwined. And if you do one, you'll do them all. If you prevent failure, you're increasing safety, and safety is always the number one priority of any organization. If you prevent failure, you will improve the asset performance, and if you fix before fail, you will get a financial benefit. Many years ago, we looked at a set of statistics, more from the UK than anywhere, where we determined that the root cause of unexpected substation failures, so the blowout, if you like, such as we see in the compound insulated cable box that's gone on the picture here, was 85% of those failures were generally associated with insulation breakdown, on which partial discharge is going to be a factor. So that's really why companies will carry out this testing. But you found PD. So you've gone out there, you've done handheld testing, you've got a monitor, you've found some signals. The question is always, when will it fail? And the answer, unfortunately, is it depends on quite a number of factors. So let's talk about this, the RCM type theory that will, I'm sure a lot of people will be familiar with, the P2F curve. The P2F curve, defined by Mowbray and others, it's all about the probability of finding, or the timeline between when you can actually see a failure starting to happen. So you're getting an indication that there's a problem. So the point at which that defect can be detected to the time when it actually failure occurs, and how long that is depends, it dictates your interval. So if you're doing an RCM study and you've got a very, very defined failure mechanism, you've got a relatively small number of variables, defined failure mechanism, you can come up with a P2F interval indication that is pretty solid. So for example, if you had a defect that always took 3 months to manifest and go from when you can see it to fail, then typically the interval of testing would be a minimum of half of that. So you'd want to be testing every 6 weeks or so. But PD is, as we've seen, there's a number of different types, and every partial discharge defect will have a unique P2F characteristic and curve. It's going to be dependent on the type, the HV asset involved, so different designs will have different capability withstanding, if you like, PD, the amplitude, the insulation type. If we had surface discharge on a polymeric bushing and we have surface discharge on a porcelain bushing, the porcelain bushing is one that we're unlikely to get any real concern about, particularly in the open siding, because it's very much more tolerant. So the insulation type makes a big difference. The environmental conditions, if we're in a damp, humid environment, surface tracking inside of metal clad switchgear will accelerate away much more quickly. And the physical position of the discharge, is it discharge into solid insulation, metal to metal type discharge. All of these things will mean that the P2F interval is not easily defined. So managing that is difficult you can't do it on a one size fits all basis. Just going to play a short video of a PD source that was developed using and captured using monitoring. Hopefully this is playing for people. So this is a source of partial discharge that we were finding using the transient earth voltage technique in this particular case, developing in a compound or a fluid type cable box. And you can see it developing over this is over a few months, weeks and months, and you can see how the characteristic is changing, the amplitude is going, and there's different numbers of voids that are probably appearing inside that insulation at that time. And if you're testing a spot check at any specific stage on that, you could get a very different result. So if we're testing at this point here, we can see we've probably got multiple voids. We've got discharge up to around 28 to 30 dB. We're starting to get concerned about it. Just a few weeks earlier, we might have been in a completely different characteristic where we were down at 10 dB. There was very, very little indication of any serious defect. So the benefit of having monitoring on there, of course, is that we can see when a defect starts and how it progresses, whereas the spot check won't do that. So the probability, we're going to talk about the probability of finding and acting on the defect before failure. Every defect, there are a lot of unknown factors. The point at which failure first starts, or the discharge, the defect starts, the point at which it can be detected, and then that time, of course. Now, what you really want to do is have a testing interval designed to eliminate as many or reduce as many of these unknowns as possible, and lower the testing interval will increase the probability of finding a defect early. But we know that permanent monitoring is not always the way the optimum costly way forward for all types of switchgear or all types of assets, really. But the earlier we can detect that, identify and detect that defect, the longer the reaction time we've got, and the more information we have in terms of, do I need to go in there now, or what? How is it progressing over time? So all these make the question of how often we should test and when will it fail difficult, because this P2F interval can be so very variable. So let's talk about testing intervals and different regimes that people use and adopt frequently. Now, our starting point as an organization really is if you're starting testing switchgear, an annual PD test is at least a good starting point. Sort of what we would consider the minimum test, the minimum test interval. The good thing about this is you can test large numbers of assets, so it doesn't take you a long time to do a spot check on a substation. In this one, we're testing a ring main unit. It might be a 15-minute test of a ring main unit, so you can do many a day. Maybe the travel in between, depending on the distance there. So it's ideal for improving network reliability, particularly if you've got a relatively poor performing network and you've got lots of problems that need to be identified quickly, is to get it out there and test. Now, of course, the disadvantage of doing that is you're putting people in the field to test, so it requires trained, skilled people, which is time and money, of course. You need to get them trained so that they understand what it's doing. And if you're collecting all this data, you do need to be thinking about how you're managing that data and what solution you're putting in place to long-term trending. You'll get really, really valuable information as soon as you start testing, even on this basis. If you've got defects on the system that need to be taken off quickly, this will give you a very quick boost in network performance. So let's say that we decide that we need to increase that frequency. So we've got a higher criticality asset, for example. So we're going to test 1 to 6 months, every 6 months, every 3 months, whichever it may be, to decide that, to reduce that probability. So it is really good. That's the sort of thing that we would do if you've done a spot check, you found a defect, you don't think that defect is of a level where you need to act today. Then you would introduce an intermediary and maybe a regime of testing to look for trending discharge sources. The shorter the test interval, the higher the probability of finding the PD before it hits that failure and finding that defect and understanding it. Of course, you're putting people in the field more frequently again, so you still need the technicians. They're going to have to be in there, so it's slightly more costly. One thing that you're testing to be aware of, if you are testing regularly and you're finding nothing, is complacency becomes a significant testing issue. So if I'm going to the same substation every month and I'm testing and I'm finding nothing every month, am I still really doing the best job after month 6, 7, 8, 9, 10? Am I still paying the right level of attention? And that complacency can happen. Not saying that people will go and just tick the box and not do the work, but complacency can play a part. And of course, if you're testing much more frequently, then you've got much more data to handle. So the management procedures become even more essential to allow trending and everything else. Okay. So the next one is like moving up to more of using a monitor, but using a monitor on a periodic basis. When I first started working at EA Technology, which is way back in 1996, this is one of the things that we would always recommend with people, the network operators that we worked with, that we would look for testing maybe every 2 to 4 years. We would look for putting a monitor onto a switchboard for a period of, say, 1 week. Now, what that does is it does improve the probability of detecting a defect. It's not realistically, if you've got a very short P2F interval, say it's a short P2F interval of 3 months, then choosing 1 week in a year versus 1 day in a year is not massively changing your probability of detecting that defect first. But what periodic monitoring, putting a monitor on for a week does, is it allows you to test under a different set of network configurations. So switching on the network, so pumps are switching in and out on a daily basis, or swapping configuration. You're seeing the loading on the network changing from the day to the nighttime. We've certainly seen defects which are affected by load. High voltage is the primary, the stress is not hugely affected by load. It's more by the voltage, but in certain times where the load goes high, you might get some expansion and contraction of certain components. So we've seen load related defects. So testing over maybe a week with different loading conditions, different environmental conditions, can give you information that you're not going to get from a spot check. Of course, disadvantage of using this system is higher hardware cost, and then you need the technicians to move the systems around the site. So it's the time element again. And then you get to the ultimate. There's a big trend in the industry towards permanent monitoring of condition monitoring, partial discharge, and other techniques, basically. And this is great in the fact that it provides you the highest probability of finding the partial discharge defect at the earliest stage. So you can see when it started. I mean, if you put a monitor on and you've already got PD there, you don't know when it started, but you're looking forward. So it allows for years of data to be easily trended. It gives you fast response time. So if something happens, you can be warned very, very quickly. And of course, you've got all the network configurations, environmental conditions, and everything else. The good thing about it from somebody like my point of view is that if I've got a monitor on a switchboard I need to assess, I can do that from the office here at any time of the day, rather than having to travel to site and everything. But it does reduce the time spent inside the switch room. Typically, a switch room is going to be safe because the probability of failure is still very low, but it's still more safe to be in an office environment than standing in front of the switchgear. But of course, there's higher hardware cost involved in that, so it's not always full permanent monitoring of condition is not always practical on that space. Okay, so let's have a look at a couple of the case studies so that we can see how the different scenarios would play out. The first one here is on an 11 kV ring main unit. It's in an airport. The network had done annual partial discharge surveys of all their HV assets, and in this particular instance, they'd replaced an oil-filled ring main unit, 11 kV ring main unit, with this SF6 ring main unit. What they'd done at the time, though, is not replace the HV termination. So instead, they reused the original PILC terminations, paper insulated lead covered cables, those original terminations, and put a new ring main unit on top. Now, the new ring main unit was tested annually for a 4-year period, and then partial discharge was detected. On the 4th year, a medium level source of PD was detected. Fortunately, before they intervened, termination failed some 7 months after the PD source was identified. We look at the picture of the failure. I mean, the reason it wasn't acted on was that it's actually quite a difficult one due to network constraints to take off. And it's that balance between probability of failure versus network disruption. And can I wait for my next outage? So can I wait for the next annual shutdown to come along or not? In this particular case, the decision was made to wait, but unfortunately in a 7-month period it failed. So it occurred in the trifurcation of the PILC joint at the bottom here, and we ended up with an unplanned outage of that critical infrastructure. In this particular instance, this is an ultrasonic trace measured in decibel microvolts. It's not a huge level of discharge, but the difficulty with ultrasonic is the level of discharge you find on any one day can be very much changed by the level of humidity in the environment. So on a dry day, you'll get a lower signal than on a humid day. So you have to be very careful for that. And trending surface discharge as it moves towards failure is also very difficult, if not impossible to do. So let's think about that on the timeline on our testing type intervals. The ring main unit was installed 2017. We tested in 18, 19, didn't in 20. There was something else going on around that time. 21 we did, and then July 22 we found that level of discharge. So the discharge was there not in July 21, but it was in 22. So what we would probably say with a P2F interval in this is your minimum interval is it just started the day before we were there, or the day we were there. So the minimum interval from when you could see it to the failure was a period of 7 months. The maximum, it started the day after. It started the day after we left in 2021, and that would be a 19-month period. So the P2F interval in this is probably somewhere in that region, 7 to 19 months. So the chance of detecting using annual survey is relatively high. Chance of detecting using permanent survey is very high. And if you were to test every 6 months, you'd definitely be finding it before failure. Okay, let's look at case study 2. This is on 11 kV voltage transformer that we say failed. It didn't actually fail. The failure was prevented. So the functional failure occurred. So the switchboard would have been installed circa 1975. Due to its criticality, I've got permanent monitoring on there since 2016. Now, during the first 18 months of monitoring, no partial discharge sources were detected on this VT. So if you think about that, if I was testing on an annual basis, I was going in there and on not an annual basis, on a monthly basis, going in there testing, am I detecting nothing? I'm getting nothing for 17, 18 months, and then all of a sudden I've got something. So a high-level source kicked up in August 2017. The client was notified and an outage was planned. We can see in the graph here, this is what was happening. So again, this is an ultrasonic source measured in decibel microvolts. We're reading negative numbers, which is very, very low or nothing effectively. And then on this one day, which is a Friday afternoon, it will always happen on Friday, we had a burst of activity. We went from -2 dB on an average to an 8 dB on an average. That's quite high in terms of average numbers. And then the client was informed here. Now, the outage was planned, but it was planned on a couple of weeks later, on the 19th. And when it was taken out of service, you can see we've got major sooting, burning on the VT. We've got big cracks in the insulation here. So we're going to be relatively close to disruptive failure occurring at this point. Let's think about that in terms of our timelines. We started the monitoring February 16, and we've got the defect detected in August 17. And the switchgear is obviously there since 75. And 2 weeks later, we've got it in that state. If you look, or if you think about how degraded that was, how much sooting, the blackening, pitting, and the cracks in that insulation, we'd estimate that probably you've got maybe a 1 or 2 month period before it fails. It may last a little bit longer. It may last just a couple of weeks. So you've got a very short P2F interval on that. So let's think about that from, let's say it was a 2 month interval. So we will be generous and say it would last 2 months. If I'm doing an annual survey, then maybe I've got roughly 1 in 6 chance of finding that using an annual survey. So that's where you might get the instance, and you do come across it, where companies will say, well, I've had a failure. I look back at my old test results and we saw that we tested it 6 months ago. We had no evidence of PD. So why has it failed now? And what tends to happen at that point is you get one of two reactions. One is they'll blame the person who was testing whether they did it properly, or they will put into disrepute the effectiveness of doing testing in the first place, or any condition monitoring, realistically. And when you think about it, if you look in this instance, would the person have found the problem? No, because 6 months ago it wasn't there. And is the technique relevant? Absolutely, because we've just seen that we've found and detected the problem here. Big issue in that particular instance is that P2F interval was just too short for the testing regime that was in place at that time. Okay. So coming up towards the end to allow time for questions. So the summary and conclusions on that is that every PD defect has a different P2F interval. So what you need to be thinking about is designing the test regimes. Yes, they need to be there to identify the sources as early as possible. And if you decrease the testing interval or put permanent monitoring on there, you will detect more of these short P2F intervals. However, that may not be the most cost-effective solution for whole large networks. So what you then do is you change things and you start looking at what is the risk on the network and what is the criticality of the assets I'm dealing with. So therefore, we're going to reduce our probability of failure on the critical assets by doing more frequent testing or putting a permanent monitor on in that. But on some less critical assets, we will accept that there will be certain instances where we will have we will miss things. So if you think about some of the networks, so the UK electricity networks, for instance, may do annual testing of primary substations or even 6 monthly testing of primary substation switchgear. When it comes down to a distribution network, they might test that every 2 years to 5 years. What they're really allowing there is yes, they will accept a slightly higher probability of failure on those distribution assets because consequences and criticality are not as much, and they do accept that you will miss some of these shorter P2F intervals. So my final slide, just to say the answer, which is depends, of course, is that understanding the consequence of failure allows you to determine the most cost effective. But if you want my recommendation of where you would start, then lower consequence assets, you would look for maybe every 2 years or every year if you haven't got that many of them. Electricity industry, maybe every years, for example, with volume. Medium consequence assets, you would look for a shorter, so annual or 6 months. And if you've got high consequence assets or high risk assets, then the shorter the interval, the better. 1 to 3 months if you've got a handheld and you don't want to put permanent monitoring on, or permanent monitoring is the way to go, because that will give you that best probability of detecting all the failures. So at that point, just leave you with that slide. So if anyone does want to connect with me on LinkedIn or receive any educational materials on this, then those QR codes are there and available. But at this point, I think I'm going to be handing over to Tariq to do a question and answer. Yes?
Yeah, thanks, Neil, for your talk. We have few questions here. The first question I have is the false positive and false negative rate over the fleet to see how cost effective it is. Not so much specific examples.
Yeah, so the false positive, false negative, it's always a challenge, of course, and people do get relatively worried about interference coming in and things like this. Nowadays, it's a lot easier to identify whether it is interference or a positive partial discharge. So when I first started, really, you're looking at amplitude was the one factor you had. So you were measuring a transient earth voltage and you got an amplitude figure. Then we went from amplitude figures to amplitude and pulse rate, so you could see what maybe if you got very high pulse rate, it's more likely to be electromagnetic interference. Nowadays, you've got all the phase resolved partial discharge plots come out of virtually all instruments on the market that are decent anyway, ours and others, and that allows you to determine is it consistent with PD. So you will get certain interference. So if you're testing on certain types of assets, you maybe inverters will give you quite high interference noises. But it's typically, you can do some testing that goes underneath that, and the interference noise is normally below the level that we would say to intervene in and carry out maintenance or rectification anyway. So realistically, with good instruments and good engineering judgment and analysis of the data, then it's not that big an issue. And you've also got that thing that you depending on the safety and the criticality, you would err on the side of caution as well. Okay.
Yeah, the next question is, how does PD relate to TD measurements? IEED PD low, but TD is high. How can you predict cable failure?
The two complementary but different. They're two very complementary but different techniques. So the tan delta measurement on a cable, if you're doing that, I mean, this is offline testing, of course, for tan delta and maybe VLF testing on the cable system. If you've got a wet cable, so you've got the moisture in there, that's what you're going to detect via tan delta testing. It's a bulk measurement, mind you, with a tan delta. So if you just got one wet section, you don't know exactly where. But that's not necessarily going to be giving you partial discharge. So you will, whenever we do offline testing of cables, we would always do both techniques, tan delta and PD, because they may be completely different to each other and independent. So PD is not going to find the wet cable. The tan delta is not going to find partial discharge.
Okay, thanks. Next question is, what would be the PD monitoring interval for 33 kV XLPE cable to ensure detection of defect prior to its progressing to point of failure?
Yeah, well, there's 33 kV cables. So we've got permanent monitoring on quite a few 33 kV cables, in not in the Australia business, but in some parts of it. And again, we've had instances there where we found partial discharge, and it was a case of, can we wait for an outage? And the outage, I think, was something like 9 months after the point of which we detected the PD. So it was an annual outage in that facility, and they detected it, and then they decided to wait 9 months and look for trending. In that particular case, it worked because the P2F interval was longer than 9 months. If you were to get a defect in the bulk of the cable, so what I'm talking about in that example was a defect was on the XLPE joint, 33 kV XLPE joint. If you were to get a defect in the bulk of the XLPE cable, then realistically monitoring or anything isn't going to give you enough warning time, because if discharge happens in the XLPE cable, you will accelerate to failure very, very quickly. So when you are testing XLPE cables, 33 kV, 11 and above, really, you're only monitoring on discharge at the joints or the terminations. Depending upon the level of discharge that you find, we would indicate how quickly you need to move. So, for example, if you had a 1,000 picocoulomb level of discharge on an XLPE joint, you'd probably say that it's going to last a few months, if not 6 months, a year. If you have 2,500, 3,000, 4,000 picocoulombs on an XLPE joint, 33 kV, then we'd say that you need to intervene within the next 3-6 months at the minimum. So it's another one where it depends, but testing interval. If you've got no indication of PD at the moment, then at the very least, say an annual test is a good starting point. Yeah.
Okay, thank you, Neil. Neil, we have another question from Greg Stone. Case study 1 was one of the sensor TEV. What dB level above background was moderate PD?
Hello, Greg. Good to hear from you again. The case study 1, I'm going to flip back to it because I think it was actually not a TV, Greg. I think it was. Sorry, I'm button happy. Right. So no, it's an ultrasonic one. So because it's surface to surface between in that spacing on the cable, basically on the pilk, that's 20 or so decibel microvolts. So that's an ultrasonic measurement. If I remember rightly, we did find some TeV on there. The background reading on this network is usually about 5 dBs, so very, very low. So it's easily identifiable. But this particular trace that we've got here is a ultrasonic trace. The probabilities of getting a background reading, just to add slightly to that, the probabilities of getting a background reading much greater than about 20 dB are only about 7% or so based on stats. By the time you get to about 29 dB, which is sort of the red level for TeV reading, then it's usually about 1 or 2% that you will see background readings up there. But the PRPD plots allows us to really overcome that nowadays.
The participants can raise their hand if they have question. I can unmute. Okay, we have another question from Stan. Will the TD lead to PD before failure?
Good question. Maybe. Not necessarily, actually. If it's a wet cable, and it depends if it's XLP cable, wet cable that causes water trees, the water trees will typically go to electrical trees before failure. But again, will you get any massive warning on that? The answer is probably no. It'll be very fast failure mode. If you're looking at tan delta on PELK cables, I guess it's possible. It's always possible, but it's not necessarily true. I mean, you're looking at when you get in the high tan delta region for a stable system and a cable system, it's probably a sign that you've got sheath damage and the water and moisture is coming in there and things like that. And you might have to cut out a significant section of the cable to do that. It might lead to PD, but it's not 100% necessarily that it will.
Okay, we have another question. For the PRPD plots, how get the 50 Hertz AC synchronous signal and how no phase relationship of the phase with the PD? Are this part of the experience that is needed?
Yeah, no, the 50 Hertz, right. So when you get these PRPD plots, you will always try and get a reference to the phase angle, to the phase. When you're using handheld instruments, then normally you'll either grab a phase reference from a fluorescent light, you'll grab it from the E field, you'll grab it from a Rogowski coil or something like that, and you'll basically sync the instrument you're testing to a 50 Hertz signal. And it's the local 50 Hertz signal. What you don't actually know is which phase you're measuring. So if you're measuring on a piece of switchgear or a cable and you're measuring red, white, blue phases, then you know that your PRPD plot will be locked to a 50 Hertz or 60 Hertz signal, but you won't necessarily know which phase. But what you're really interested in is interpretation of the PRPD. You're interested in how that looks. So if I can go back to the only one we've got in this presentation, really, you've got a distinct cluster around just after the 270 degrees, and you've got a distinct cluster here just before the 90 degrees. The reason this is quite long, if this was a single phase event, you would get a distinct hump in the two clusters at the 180 degrees separation. The reason we're seeing this quite long clustering here is because we're looking at phase-to-phase type discharge, so more than one phase is involved. So there's a lot of things you can interpret from the PRPD plot. You can interpret, is it corona? Is it internal void? Is it surface type discharge? Is it contact discharge? How many phases are involved? All of these things can be interpreted through experience, as long as you make sure you're grabbing the phase reference and you're referencing all the measurements you're taking to a 50 hertz, local 50 hertz reference. You can easily do this, in all honesty, if you've got partial discharge in the field and you're measuring and you can't grab from a true 50 hertz reference, then you can usually tune the instrument by going into a manual mode and just seeing which way the clusters will go, whether they'll drift left to right, and you can adjust the frequency to get the clustering to be steady. So what you're typically looking for on any PRPD is two clusters of activity 180 degrees apart with a stochastic type, so slightly random around that same point of 180 degrees apart. So stochastic nature on the PRPD. You can interpret a lot from the PRPD plots nowadays.
Okay. Any other question from the participants? Okay, thank you, Neil. Thank you very much for your time and giving us a detailed insights into PD measurement. Yeah, that's done for today. Thank you very much.
No problem at all. Happy to help.
Cheers.
Thank you.
Thank you. Bye, everyone. Thank you.